All right, so a couple of things here before start off the lecture today, okay? The first is kind of I just received the notice from Apple level kind of office, okay? So they ask kind of the final exam has to be kind of done by the Thanksgiving week, okay? And original our final exam, the date is Monday, the November 30th, I remember. Okay, so that's not optional now. Okay, so I'll think about it. Okay, so when do we have kind of final exam? Okay, and then give you guys some kind of update. Okay, but if you need some kind of travel, book you flight for winter, okay, that's fine. Okay, doesn't matter. Okay, because even you miss scheduled kind of final exam date. Okay, so we can do it kind of in later time or early days. Okay. All right, and then second thing is kind of this week lab. Okay, so this week lab will be a tough one. Okay, and be prepared. Okay, so we'll take more than 3 hours. Okay, take more than 3 hours. Okay, so if you in the evening lab section or kind of for example Wednesday evening and also Thursday evening lab section, my suggestion kind of get some dinner or some snackers, okay, before you come to lab, okay. And if you are also same thing for the Friday non-lab section, okay, get some kind of food, okay, before you come in, okay. And make sure that when you do the experiment, okay, read the old reagent bottles, okay. So we'll use kind of both the regular ether, we call kind of wet ether, okay. Also the anhydrous ether, we call the dry ether, okay. So very beginning, you set up your reaction with kind of dry ether, okay. Don't use wet ether, okay. So that's the key thing, okay. How much longer do you think, okay? How much longer? I don't. So like maybe. Depends individuals, okay. So if you did everything right, okay, so probably full 3 hours, okay. But most of your guests kind of 3.5 hours, okay, at least, okay, And make sure all your glassware are dry, okay. So the tiny amount of the water will kill you the green ion reagent, and you will get kind of very poor yield, okay. And the key steps kind of actually first step, okay, so you need to initiate your reaction, generate kind of the green ion reagent, okay. So the right observation kind of you see a lot of bubbling, generate kind of your magnesium kind of the metal, okay, so the chips, okay. That means kind of you have good start, okay. But if you didn't see any kind of the bubble from kind of reaction solution, that's fine, okay. So just dump all the kind of the solution, okay. And then don't clean your glassware, just go ahead kind of redo the reactions, okay. So won't waste you too much time, okay. Don't clean your glassware, okay. And so that's something, okay. So again, okay, make sure all your glassware are dry, okay. All right, okay, so some students have some question about the post lab, okay. So I will keep this Zoom open, okay, after the lecture, okay. So if you have any question about the post lab, okay, please stay on the kind of the Zoom, okay. Leave your Zoom open, okay. You can ask me questions then, okay. All right, okay, so now we can start kind of the chapter 19, okay. All right. So remember, okay, so in the chapter, actually the chapter 19 is kind of called the substitution reaction of the carbonyl group, okay. So if you have a question, again, you can type in the chart window, okay. All right, so chapter 18, okay, so that's actually kind of the reaction of aldehyde ketone, okay. So we call it kind of addition reaction, nucleophilic addition reaction, okay. So you have kind of the aldehyde or ketone, okay, and then some nucleophile coming in, okay. Attack the carbonyl carbon, okay. And once reaction is done, okay, you generate kind of addition product, okay. All right, nucleophile go here, okay, and then oxygen will pick up the hydrogen, okay. So that's the easiest one, okay. Yeah, this is recorded, okay. This is recorded, I think so. Yeah, all right. Okay, and So that's here the chapter 18 reaction, okay? So for chapter 19 reaction called the substitution reaction at kind of carbonyl group, okay? So especially about here all about kind of your reaction of here the carboxylic acid and also its derivatives, okay? So so the general reaction for this chapter, okay? So what happened kind of something like this, okay? All right. So L is a leaving group, okay? So maybe I use another color, okay? Normally we use kind of a blue color labeled kind of leaving group, okay? All right. And then again, so this time still some nucleophile coming, okay? Use the red for the nucleophile, okay? All right, so after reaction is done, okay, so the node addition product is substitution reaction happened, okay. So the nucleophile replace the leaving group, okay. So that's why we call it here the nucleophilic here the substitution reactions, okay. So you see difference. One's addition, chapter 18. One kind of substitution reactions, okay. All right, and then before we talk about the reaction of this chapter, first a little bit the review of carboxylic acid and also carboxylic acid derivatives, okay. So carboxylic acid kind of just the two attachment on carbonyl carbons, okay. One's alkyl group, another kind of OH group, okay. And then we have kind of four carboxylic acid derivatives, okay. First one kind of acid chloride, also called acyl chloride, okay. So this time kind of chloride attached kind of carbonyl carbon, okay. And then for the acidic anhydride, okay, so that's actually kind of the whole we call kind of carboxylate, okay, this whole part, okay, attached kind of carbon carbon, okay. And then esters OR group, okay, and then amide kind of the amine, okay. So there's the one the carboxylic acid derivatives actually nitrite, okay. Nitrite, doesn't have kind of the carbonyl group, okay, but the nitrate has a very similar reaction as other acid or acid derivatives, okay. So that's why we will learn the nitrate reaction also in this chapter, okay. Right. So for all these acid also acid derivatives, okay, so most of them have kind of this part we call the acyl group, okay. A difference in the actual kind of the happen another part, okay. So that's we call kind of leaving group, okay. So that's the most important kind of this guy, okay. That's determine kind of what reaction they can have, okay. So and how they are the kind of reaction rate, okay. Right. And so like labeled here, okay. So depends what's its kind of what kind of acid or acid derivatives, okay. So the leaving group can be OH, okay. So that's for the acid, okay. And then can be kind of the chloride, okay. So that's for the acid chloride, okay. And also can be kind of carboxylate, okay. Also called kind of the carbonate, okay. That's for the anhydride, and then OR minus, okay, for the ester, and then the amine, okay, amide, okay. So for the amide, okay. So can be kind of NH2, NR2, or NHR, okay. So either is fine, okay. Right. And for the general mechanism for this chapter, actually kind of although it's called the substitution reaction, actually kind of the little bit different from kind of the SN1, SN2 reactions, okay. SN2 reaction is kind of directly nucleophile coming in, replace kind of leaving group, okay. And then SN1 reaction, leaving group is gone, and nucleophile coming in kind of And for the carbonyl substitution reactions, okay, so the general mechanism, okay, depends on what reaction conditions, okay. So if it's kind of under basic conditions, okay, so it's will something like this, okay, so so this reaction, can happen under either acid condition or basic conditions, okay, so we'll learn them kind of one by one. So basic condition, okay. So basic conditions kind of normally happen for kind of strong nucleophile, okay. All right. Negative charge species, okay. It will attack kind of carbonyl carbon, open the CO bond. All right. And the ones kind of the lone pair electron on oxygen go back, it will kick off the link group, okay? And give you final kind of substitute product, okay? And so for the from here you can see the difference of the nucleophilic kind of carbonyl substitution reactions kind of the generally kind of this we call the tetrahedral kind of the intermediate, okay. And that's different from SN1, SN2 reactions, okay. Narrow generally kind of this intermediate, okay. And also for this reaction you can see kind of pretty much two-step reaction, okay. So the first step actually kind of rate determining step, okay. So the first step kind of actually kind of addition reactions, okay. So that's the rate determining step, okay. Yeah. Or kind of we can call kind of rate limiting step, okay. So RLS, okay. And the second step kind of elimination, okay. So that's happening pretty fast, okay. All right, and then also showed here, okay, so depending on what kind of the acid or acid derivatives leaving group can be all this, okay, also showed here, okay. All right, so that's under the basic conditions, okay. But if you have kind of some the weak the acid, okay, or kind of weak nucleophile, okay, to do the kind of nucleophilic substitution reactions, okay, so that's you get kind of the under acid conditions, okay. So we also call kind of acid kind of mechanism, okay. All right. So for acid mechanism, okay, so like I said, kind of some kind of weak nucleophile, okay. So weak nucleophile, normally you cannot directly attack kind of this the carbonyl carbons, okay, too weak, okay. So you want to activate kind of this carbonyl carbons, okay. And in this case, that's why it's an acid condition, okay. The first step, okay. So the oxygen will pick up the hydrogens, okay. So protons, okay. Pretty similar like we learned kind of the acid condition of the carbonyl addition reactions, okay. All right, once you have this, okay, so that's we call it activated kind of carbonyl compound, okay. And then nucleophile come in, okay. So nucleophile normally kind of very weak one, neutral one has kind of proton with it, okay. All right, and then open the sealed about, okay. All right, and we also generally is called kind of the tetrahedral intermediate, okay. Okay, so for this tetrahedral intermediate case, so there's kind of the intramolecular kind of proton transfer, okay. So the leaving group will pick up the hydrogens on the nucleophiles, okay, and then convert kind of back to the group, okay. But if you want to do kind of the intermolecular one, okay, so that's also fine, okay. Intermolecular one kind of you do it two-step, okay. Some base come in, pick up these hydrogens, okay, and then some kind of weak acid come in, okay, deliver this hydrogen to kind of the leaving group, okay. That's also fine, okay. But either way is kind of no problem, okay. All right, so once you done this, okay, so now the nucleophile become neutral, okay, and then the leaving group, okay, pick up the hydrogen, okay, become kind of positive charge, okay, better leaving group, okay. All right, so next kind of lone pair electrons on oxygen shift back, okay, kick off the leaving group with the protons, okay. Yeah. Right. After reaction is done, okay. All right, so like this, okay. But there's one more step, okay. This is the positive charge, okay. So you have to pick up these protons, okay. So any base, okay. So so pretty much just solvent, okay. So normally speaking, pick up these protons and then give you back kind of the neutral molecule in the end, okay. Yeah. So that you can see kind of for the acid conditions kind of the more complicated, okay. And also normally speaking kind of for the acid conditions, okay, so the whole steps kind of reversible, okay. And so yeah, that's the difference between acid and also yeah basic conditions. Okay. Basic condition pretty much yeah you push it to the end. Okay. All right. So here's yeah some questions. Okay. So yeah. For the aldehyde ketone have the carbonyl yeah groups okay for the acid and also acid derivative okay also have kind of a carbonyl group okay. Why aldehyde ketone has kind of the yeah addition yeah reaction product okay so shown here okay, but for the yeah acid or acid derivatives have kind of the substitution product okay. The reason actually kind of yeah pretty easy okay because the aldehyde ketone yeah don't have kind of yeah good link group okay. So for aldehyde ketone case, yeah, if you want to do kind of elimination reactions, okay, so in the second step, they get kind of yeah, give you back kind of carbonyl compound, okay, so yeah. So that means kind of yeah, lone pair electrons on opposition need to go back, okay, and kick off kind of yeah, the hydride or we call kind of yeah, carbon anion, okay. So that's here yeah, these two guys kind of very pooling group, okay. So H minus or R minus, okay. That's here the very strong base, okay. So that's we just learned before, okay. So impossible, okay. So that's here the means kind of yeah, pretty much yeah, you stay at kind of yeah, yeah, just addition stage, okay. So yeah, kind of yeah, here, okay. You stay at kind of here or here, okay. So that's it, okay. But yeah, for the yeah, acid or acid derivatives case, so yeah, because yeah, the leaving group kind of yeah, the relative kind of yeah, the yeah, active case, so yeah, the easy to leave case. So that's why kind of you can to push one more step, okay. We call kind of elimination, okay, kind of final yeah, the final yeah, kind of yeah, the carbonyl compound, okay. And for the yeah, all the acid derivatives, okay, so they don't have kind of yeah, the same kind of yeah, reaction rate, okay. So yeah, it really depends on how good is the yeah limb group, okay. And here kind of yeah two effects involve kind of the yeah how good the limb group is, okay. So one is the yeah inductive effect, okay. So limb group kind of the yeah good or poor, okay. Yeah. So two effects, okay. The first kind of called the inductive effect, okay. So yeah, inductive effect pretty much means kind of the yeah how strong of the ethylene group kind of yeah pull electron yeah to itself, okay. And theoretically speaking, kind of if you have kind of the electron withdrawing group, okay, so yeah yeah want to polarize kind of this bond, okay, carbon link group bond, okay. So eventually kind of the increase the rate, okay. But yeah, if you have kind of the yeah electron donating group, okay, electron donating group kind of donate electron to the carbons, okay. So first make the carbon kind of last kind of electron 5, okay. And second kind of you have kind of the yeah maybe some weak kind of pi bond between the yeah carbon and also the link group, okay. So that's yeah decrease the reaction rate, okay. So for you guys, yeah, just remember, okay. So yeah the yeah electron donating group, okay, decrease the reaction rate, okay, and then electron withdrawing group, okay, increase your reaction rate, okay. Yeah. So that's the yeah effect, okay. And then second effect kind of yeah resonance effect, okay. So yeah, if there's kind of yeah lone pair electrons on kind of yeah the yeah link group, okay, so yeah you can have kind of yeah resonance kind of yeah structures, okay. Yeah, with lone pairs, okay. And then yeah, that's lone pairs adjacent kind of yeah pi bond, you can push electron twice, okay. So you can see kind of here the yeah, resonance effect actually kind of here you have here the more pi bond kind of factors, okay, between kind of here carbon carbon and the link group, okay. So pi bond kind of here the relative kind of here quite strong here because there's that bond, okay. So that means kind of resonance effect actually kind of here decrease the reaction rate. Yeah. So all right. So yeah, for most of the yeah link group case, so they have kind of both effect, inductive effect and also the yeah resonance effect. You have to see which one play the major role, and then which one kind of the yeah will determine kind of how good of the activities. Right. One example showed here is the yeah acyl kind of chloride, also called kind of acid chloride. Okay. Yeah, if you guys have questions, just type in chat window, okay? And then yeah, the fluoride case, so yeah, pretty strong kind of the inductive effect case. So yeah, the chloride kind of the pull electron away from kind of carbon, make kind of polarize K, and then eventually break up K. So that's increased reaction rate K. And also have kind of a resonance effect K. So they are build up kind of a CR bond K. So that's will kind of a decrease reaction rate K. And for the chloride case, so this case kind of the inductive effect will play the major role K. Compare with kind of the resonance effect K. So that's the inductive effect win kind of resonance effect K. So that means kind of the acyl chloride kind of actually the pretty good link group K. You have kind of the CR K. On the other hand, okay, so you can think about kind of the similar like the S1 SN2 reaction we learned kind of normally speaking kind of if the Lie groups kind of the weak base, okay. Right, so that will be kind of a good link group, okay. And so weak base kind of don't like kind of go back to the original state, okay. Be happy with self, okay. So it's very stable, okay. More stable, okay. And then easy to leave, okay. So easy to leave, okay. So that means kind of the high reaction rate, okay. Okay, so that's actually kind of same as the S1 and SN2 the link group, okay. So some questions, okay. Well, weak resonance decrease, yeah. Okay, so resonance effect, no matter strong weight, okay. So decrease the reaction rate, no matter kind of the and no matter strong on the weight, okay. So yeah, normally speaking, kind of you want kind of let's see that. Okay, so yeah, the weaker the resonance effect, okay, cannot kind of overcome the inductive effect, okay, and then yeah, you have kind of a good link group and increase reaction rate, okay. And but yeah, if you have kind of the strong resonance effect, okay, so that's will play major role, okay, yeah, and then we'll kind of kind of give kind of very poor reaction rate, okay. So no matter kind of strong or kind of weak resonance effect, always decrease the reaction rate, okay. Always decrease the reaction rate, okay. But these two, okay, so inductive effect kind of resonance effect kind of you have to kind of compare these two, okay, so yeah. Yeah, that's right, okay. No matter the resonance effect, always kind of decrease the reaction rate, okay. Inductive effect, okay, so theoretically speaking, always kind of increase reaction rate, okay, so yeah, just kind of how degree kind of it's if electron withdrawal group, okay, will kind of increase a little bit weaker, okay, so increase, okay, so yeah, and then electron withdrawal group, okay, kind of increase kind of more than kind of electron donating group, okay. Right, and then go back here, okay, so the acyl kind of chloride kind of most reactive kind of the capacity, okay, so and also derivatives, okay, because the CL we know that kind of miners kind of very weak kind of the very big base, okay, so very good link group, okay. Right, and then give you guys kind of another extreme situation kind of amide, okay. So amide, okay, so NH2 okay, has also both inductive effect, okay, and also the resonance effect, okay. So yeah, like I said, okay, inductive effect, okay, increase reaction rate, okay, and then for the resonance effect, okay, so yeah, decrease reaction rate, okay. So yeah, but yeah, this time kind of resonance effect kind of the win, okay. So they have kind of play major role, okay. Yeah, because we know that kind of lone pair electrons on the nitrogen kind of easy match with kind of orbital of the carbons, okay, in kind of same period, okay. Yeah. And in this case, okay, so resonance effect, okay, win kind of win over kind of inductive effect, okay. So that's the overall amide we have kind of will be kind of the poor reaction rate for the nucleophilic carbonyl substitution reactions, okay. And we can also try to understand this one in another way, kind of how good is kind of link group, okay. So for the amide case, so amide case, so the link group kind of NH2 minus, okay. That's we already learned in the previous chapter, okay. Very strong base, okay. Strong base or it's kind of proline group, okay? So they want to go back kind of the attack the carbonyl carbons, okay? And then proline group, okay, that's pro yield, okay? And then amide kind of the actually kind of the lowest the reaction species, okay? So reaction species with lowest reaction rate, okay, for all the kind of the carbonyl compound, okay. All right, so that's for you guys just remember, okay, so the resonant factor decrease reaction rate, okay, and then inductive factor increase reaction rate, okay, and then when you compare kind of which whether kind of totally increase reaction rate or decrease reaction rate, okay, you'll see kind of which one play major role, okay. And another way to compare kind of maybe either is kind of look at kind of a link group, okay. If it's a good link group, okay, you have kind of highly reactive kind of species, okay. If kind of pooling group, okay, the pool reaction species, okay. Okay, so we are talk about a lot about kind of the link group ability, okay. So the casing is here, okay. So when we compare kind of link group the ability for the all the acid and acid derivatives, okay, so you find kind of in this order, okay. So chloride kind of the weakest base, the best link group, okay, followed by kind of carboxylate kind of we see kind of medium kind of base, okay. And then followed by kind of the OH minus and OR minus, okay. So those two from carboxylic acid and also the ester, okay. So these two are pretty strong base, okay. We already know that kind of these two have kind of similar kind of basicity, okay. And but the strongest ones kind of the NR or NH the 2 minus, okay. So that's we already know kind of amide, okay. So the basicity in this direction, and then the leaving ability for this link group kind of in another opposite directions, okay. And then so that means kind of the stability for their kind of original kind of acid or acid, okay. So in this order, okay. So the acid chloride kind of least stability followed by kind of anhydride, followed by kind of acid and also ester, okay. And the most stable one kind of amide, okay, because the amide has a poor link group, okay, won't leave, okay. But the acid chloride has kind of very good link group, won't leave, okay. And overall, okay, so you have kind of reaction kind of the stability, okay, reactivity, okay. So in this order, okay. So that's maybe write down, okay. So also record in your notebook, very important, okay. So the most reactive one should be kind of acid chloride, also called acid chloride, okay. And then followed by hydride, okay. All right. Okay, so and then followed by kind of the acid and also ester, okay. So these two have very similar kind of reaction rate, okay. Okay, and then least reactive one should be kind of amide, okay. All right, so write down, okay. So that's the one of the key the knowledge for these chapters, okay. So their reactivities can also determine how easy we can convert one acid or acid derivative to another one, okay. And 99%, okay, so I will give out kind of ranking question in the future, probably let's see, quiz 5, okay. Ask kind of give you a bunch of acid or acid derivatives, okay. Ask rank their kind of reactivity towards the acid kind of towards kind of carbonyl nucleophilic substitution reactions, okay. So that you need to use this ranking, okay. All right, did you guys write down? Okay, so that's the key thing for this chapter. The reason for that kind of how good they have kind of different ranking, that kind of the link groups, okay. All right, and then here's also actually kind of we generate the code the reactivity the letters, okay. So the highest one kind of the acid chloride followed by kind of hydride and ester acid and also amide, okay. And the actually least reactive one we call kind of carboxylate ion, okay. The reason for that kind of the O minus is very kind of strong base, okay. But if you kick it off, okay, become kind of O minus 2, okay. So that's even proline group, okay, and then very strong base, okay, because they have kind of 2 negative charge on one atom, okay. That's normally impossible, okay. So why we will study this guy, okay, because later we'll compare their kind of reactivity, okay, use this one as kind of intermediate, okay, and determine some reactions, okay. So yeah, again, remember this kind of ranking of the reactivities, okay. All right. And so for the stability letters, okay, so that's also kind of tell you kind of it's relative to easily convert kind of the reactive species into kind of last reactive one, okay. And then, but yeah, not vice versa, okay. So for example, okay, so yeah, if someone asks you kind of convert this the benzoic kind of chloride into kind of methyl benzoate, okay. So this benzoic chloride can be acid chloride, okay, and then methyl benzoate is kind of ester, okay. So acid chloride more stable than kind of less stable than kind of the ester, okay. So that means kind of this reaction, no problem, can do it, okay, pretty easy, okay. So we convert kind of last reactive one, more reactive one to kind of the last reactive one, okay. From more stable, last stable one to more stable one, okay. But yeah, not vice versa, okay. So yeah, if you want to convert kind of the methyl benzoate back to kind of the benzoic chloride, okay. So that's very hard, pretty hard, okay. So no reaction because this time you convert kind of more stable one to last stable one, okay. That's just no hard, okay, very hard, okay. And in this case, actually kind of you can see kind of not only kind of you can use OR kind of convert to ester, okay. And pretty much any of these the nucleophile can convert kind of acid chloride into its corresponding kind of acid or acid derivatives, okay. So for example, okay, so yeah, if I want to get amide, okay, so I just kind of NH2, okay, minus, okay, as a nucleophile, okay, so yeah, NH2, okay, and then plus or minus, okay, so that's last reactive one to more more reactive one to last reactive one, okay. Last stable one to more stable one, okay. So that's no problem, you can do this, okay. So you can convert it to kind of hydrate, okay, and also kind of acid, okay. So all the same strategy, okay. But yeah, the not vice versa, okay. So yeah, you cannot go backward, okay. All right, here's kind of the reaction outline for this chapter 19, okay. So yeah, two kind of part, okay. One is kind of just interconversion between kind of acid acid derivatives, okay. So how do you prepare acyl chloride, okay? How do you prepare anhydride? How do you prepare ester and also capsic acid, okay? And also amide, okay. So those are relatively easy, okay. So yeah, because they are pretty much based on the same kind of reaction mechanism, okay. So yeah, most important prepare kind of ester and also capsic acid, okay, because these two kind of two common compound, okay, and then very kind of interesting the mechanism, okay. So yeah, let's keep in mind, okay. And the next block kind of the other kind of nucleophile, okay, we will kind of use the hydride and also the organometallic kind of nucleophile, okay. So like green region or lithium region, okay. So those kind of very strong nucleophile, okay. So in this case, they will do a little bit different reactions, okay. So that's keep in mind, okay. So that's the relatively hard kind of part for this chapter, okay. And in this part, we also kind of summarize all the reduction reactions, okay, and then talk about kind of selective reductions, okay. And for the first part, okay, so yeah, pretty much the mechanism just based on substitution, okay. So just kind of I will show you guys, okay. The second part, why it's kind of more difficult, okay, because there's kind of one more step, okay. So yeah, addition, okay. So substitution plus addition, okay. So yeah, when we come to kind of second part, kind of we'll need to be slow down, okay. All right, okay. So now we can start kind of the first reaction of the first part, okay. So that's the prepare kind of the acyl chloride, okay, also called kind of acid chloride, okay. All right, so yeah, the reaction actually kind of we start with kind of the capsic acid, okay, as starting material, and then just acyl chloride, okay. Right, some students maybe ask, okay, so Liu just said kind of we can convert kind of least stable one to kind of more stable one, okay. But now kind of capsic acid the more stable kind of that kind of acid chloride. How do you kind of do this? Okay, so that's you give some kind of fake news, no, okay. All right, so yeah. So this actually kind of because they are here we use kind of magic reagent, okay, called kind of cyanide chloride, okay. SOCl2, okay. So the cyanide chloride kind of actually kind of convert acid into kind of another reagent, okay. So so the real species actually kind of here, okay. So so I want to show you the mechanism that's not required kind of the real kind of intermediate, okay, real species kind of like this. All right. So that's here the real the reaction species, okay. So this one, okay, the real lean group is here. So that's a kind of very good lean group, okay, and then can easily do kind of the nuclear substitution, yes, kind of carbonyl nucleophile substitution reactions, okay, and Cl, okay, minus carbene, okay, and kick off the whole thing, okay, and give you kind of final product, okay. So that's actually kind of a real kind of reacting species, okay. And for this reaction, actually kind of I like it a lot, okay, because the two byproduct of this reaction, one kind of SO2, okay, and also HCl, okay. So both kind of volatile species, okay. So after these reactions, okay, so you pretty much kind of do the road trap or do a little bit of vacuum dry, okay. So all gone, okay. So we are pretty up and with kind of clean, kind of pure kind of acid chloride, okay. So that's the cool thing about these reactions, okay. And also the remember, okay, so the cyanide chloride is not the new reagent for us, okay. So in chapter 10, okay, I said kind of whenever you see kind of cyanide chloride, okay, you should get quite excited, okay, because the only function in organic chemistry tools kind of convert OH to Cl, okay. So in the chapter 10, we learned the reactions kind of convert alcohol to kind of the alkyl chloride, okay. So we use the cyanide chloride, okay. Right. And at that time, said that kind of we will revisit this kind of this region later in chapters, okay. That's here, okay. So the only function, okay, convert OH to Cl, okay. Here, same thing, okay, OH to Cl, okay. So that's again, okay. So in the exam quiz, if you see cyanide chloride, you should get quite excited, okay. Immediately find OH group, doesn't matter kind of alcohol kind of acid, okay. So just erase OH, put CRI, okay. That's here will be sure right answer, okay. And so in addition to cyanide chloride can do this reaction, okay. So the PCl3 can also kind of the PCl5, okay, can also do this reaction, okay. So that's here the called phosphorus kind of trichloride or kind of the phosphorus kind of the pentachloride, okay. Cl5, okay. So these two kind of a little bit less common, more expensive, okay. So that's cyanide chloride, okay. Right. So that's how do we prepare kind of acid chloride, okay. So from acid can, but for the real the reagent kind of that's here, okay. So that we use kind of cyanide chloride convert an acid to better kind of remove, okay, and then we can do these reactions, okay. And then second reaction we will learn today's kind of the prepare anhydride, okay. So prepare anhydride case, so anhydride kind of last more stable, okay, and then less reactive than kind of the acid chloride, okay. Definitely you can start with kind of the acid chloride, okay. So we use kind of the more reactive one, prepare less reactive one, okay. And then here the nucleophile kind of just the little bit keep in mind, okay. The nucleophile kind of whole carboxylic acid, okay. That's a nucleophile, okay. And then this one replace kind of Cl, okay, give you kind of the anhydride, okay. That's oxygen, okay. And because this reaction and the generally kind of HCl, okay, so the hydrogen from kind of the acid, Cl from kind of the acid chloride, okay. So in this case, yeah, to push reaction kind of yeah, to the right, okay. So normally, yeah, people add into the base, okay. So most common base uses this reaction kind of yeah, pyridine, okay. So the pyridine will pick up some kind of the acid, okay, and then yeah, push reaction kind of to the complete kind of reaction directions, okay. Plus, okay, and then Cr minus, okay. And one example, yeah, the showed here, okay, so that's here the acetic acid react with kind of this one should kind of purple new kind of chloride, okay, and then give kind of hydride, okay. And give you guys another example, okay. So we have this here the acid react with the acetyl chloride, okay. Right. So for here, okay, just keep in mind, okay, so you have to keep your basic carbon framework same, okay. So right, so this part from kind of the acid chloride, okay. Oh, right, another part from kind of this one called kind of butanoic acid, okay. 1, 2, 3, yeah, 1, 2, 3, okay. So that's the final product. So normally speaking, kind of you don't need to draw any kind of inorganic compound, okay. So yeah, the inorganic product, okay. Right, so that's the most common way to prepare a anhydride, okay. And there's a last common way to prepare a anhydride called kind of the anhydride exchange, okay. So okay, so that's the first way. The second one kind of anhydride exchange, okay. So for anhydride exchange happen kind of you prepare some kind of anhydride with higher boiling point or melting point, okay. And then you start with kind of some small anhydride species, okay. So the general reaction is something like this, okay. Actually, no. So you start with kind of the carbonic acid. You want to make it kind of anhydride, okay. So carbonic acid, okay. And then you react with kind of the acetyl anhydride, okay. So let's just say 3K at 20. And then this reaction just somehow like a exchange happened, okay. And then acid, okay, so this carbonic acid, okay, replace kind of this acetyl part, okay. And then for this two acetic acid, okay, so just released, okay. Okay. So that's here this happened, okay. So for this reaction, kind of actually you can see kind of we prepare one anhydride, okay, from another anhydride, okay. So the reaction actually kind of has some kind of equilibrium, okay. So because both anhydrides similar reaction rate, okay. So to push reaction kind of to the right, okay. So normally speaking, kind of we just heat up the reaction, okay, and then distill out kind of the acetic acid, okay. So this one, okay, because this one has relative kind of low boiling point, okay. So like the 110, 120 something, okay. It's kind of burn out, okay. So once the distill out kind of the capacity, okay, so that you can push equilibrium to the right, okay, give kind of anhydride, okay. So that's actually kind of the last common reactions, okay, actually pretty last common reactions, okay. But people indeed use it kind of the distill off remove acetic acid to shift it. People normally use it kind of prepare some kind of the cyclic anhydride, okay. So you have kind of the diacid compound, okay. So the acid kind of linked by carbon chain, or kind of in this case the benzene ring, okay. And then you react with kind of the acetyl kind of anhydride, okay. And then that's the convert kind of cyclic anhydride, okay. So that's the because the cyclic structure has kind of the low entropy cost, okay. So that's you can get kind of a very decent yield, okay. So 88%, okay. So that's kind of a pretty good one, okay. But just keep in mind the anhydride, the first one kind of the better way, okay. All right. Next, the reaction will learn kind of prepare ester, okay. So that's a kind of yeah, the relatively important reaction here. Okay. Right. So for ester, okay, so that's the more stable than anhydride, and also the less reactive than kind of also the both anhydride and also chloride. Okay, so in this case, yeah, it's pretty easy. You can prepare kind of the ester from kind of either acid chloride or kind of the acid anhydride. Okay, so example showed here. Okay, so just make sure kind of you use the correspond kind of the alcohol as nucleophile. Okay, so show you kind of the general reaction. Okay, so if you start with the acid chloride, okay, so just use alcohol. Okay. Right. And after reaction is done, okay, so you get ester. Okay. Okay. So the OR from kind of alcohol, okay, and then the acid group from kind of original acid chloride. Okay. And if you want to start with kind of the anhydride, okay, so and then you still use kind of alcohol as a nucleophile. Okay. So after the anhydride kind of reaction with kind of the alcohol, okay, so you generate kind of the two organic compound. Okay, so that's a little bit different kind of the acid chloride. Acid chloride you generate kind of ester plus kind of HCl. HCl kind of inorganic compound. Okay. But for the anhydride, okay, so you generate kind of first ester, okay, and then plus another acid, okay. Okay. Okay, so you can see kind of pretty much the reaction can break up for the anhydride. Okay. Yeah, we break up here. Okay. And then this part pick up the OR give you ester. Okay. Another part pick up the hydrogen give kind of the capacity. Okay. So that means kind of in future. Okay. So if you draw kind of the anhydride react with the alcohol. Okay. So you need to draw both products, two products. Okay. Yeah, because both kind of the organic species. Okay. That's also showed here. Okay, reaction of alcohol with anhydride, you generate 1 mole of ester plus 1 mole kind of capsaicin. Okay, so that's here the two product. Okay, that's something keep in mind. Okay? That's a little bit different from other reactions. Okay, and here are some kind of just the examples. Okay, so first one kind of just the benzoyl chloride, okay, react with kind of this alcohol. The alcohol kind of part actually kind of from phenol, okay, and you generate kind of the ester, okay. And then normally for these reactions, okay, because the HCl is kind of another product, you can use kind of some base, okay, like in this case kind of pyridine, pick up the HCl, okay. So but if you don't want kind of the base, okay, okay, so you still generate kind of the acid in the good the yield, okay. And then second one actually kind of more interesting case. So you want to convert kind of the acid into ester. Okay, so acid ester we just learned kind of they have similar reaction rate. Okay, same kind of reactivities. Okay, so that's the last likely. Okay, but what we have already learned kind of convert the acid into kind of the acid chloride. Okay. So that's the acid chloride pretty easy to convert kind of into the ester. Okay. So in this case, you can do two-step reactions. Okay. First step kind of acid react with cyanide chloride, convert kind of the acid chloride. Okay. And then second step, okay, so react with alcohol, give kind of final ester. Okay. So that's the pretty useful strategy. Okay. And then last example is kind of the anhydride react with alcohol. Okay. So for this case, you need to show both products. Okay? One kind of ester, one kind of acid. Okay. Okay, and last case, so next we also kind of one of the most important kind of reaction for this chapter kind of the Fischer acidification. Okay. So this reaction actually kind of quite cool thing, kind of the one step you prepare the ester from capsaicin. Okay. So that's different from kind of your previous example. Previously you have to do 2 steps. Okay. This time kind of 1 step. Okay. And the general reaction is kind of something like this. Okay. Yeah. You have capsaicin, okay, and then react with kind of the alcohol, okay. And then under the acid conditions, okay. And then you can also produce kind of the ester, okay. And so another byproduct just water, okay. So but if you want to draw it, it's fine, okay. Just go ahead and draw it, okay. And for this reaction, kind of magic things kind of we know that kind of for the acid and also the ester, they have similar reactive activities, okay. So that's how do we control the reaction, okay? So make kind of the shift to kind of ester reactions, okay. So first we add kind of the acid as catalyst, okay, and then second kind of try to kind of remove the water, okay. Yeah. So remove water, remove one of the product, okay. So normally happen kind of you can do the distillation, okay, and also kind of some reagent drain reagent trap the water, okay. And then third way is kind of use a large amount of alcohol, just kind of add a lot of alcohol inside, okay. So in this case, can shift equilibrium to the right, okay, to right, okay. So give kind of the still decent amount of ester, okay. And for the mechanism, kind of pretty important. Okay, so but because of the time limitation. Okay, so I will draw kind of mechanism kind of in the Friday class. Okay, so so for today's class we will stop here. Okay. Yeah, phase clarification. That's one of the most important questions. The reaction in this chapter. Okay, so we'll start it further on Friday. Okay. All right, any question about the lecture today? You shift the reaction right by adding acid. Yes, okay, catalytic amount of acid, okay, catalytic amount of acid, okay. So that's related to the mechanism, okay. So I will show you kind of the class next week, okay. On Friday, okay. But the main way to shift the equilibrium is kind of remove the water, add alcohol, okay. So that's the main way to do it, okay. The Y acid kind of is catalyst, okay. So I will show you kind of on Friday, okay, show the mechanism, okay. So so the acid actually can be recycled, okay. All right, any other questions?
Could you go over question 4 from post lab 4?
Question 4. Okay, so the homework.
No, from post lab 4.
Or post lab 4. Okay. All right. Okay. So anyone has question about the lecture today? All right. So let me stop kind of recording the